So the whole idea of mip mapping, I'm just gonna gloss over it, is that there's a good video about it. I'm not gonna show it now, but basically, uh, a few things, like if you have something that's very far away, um, but it has a lot of high frequency details. And if you just sample it like the nearest thing that your sample can find, it'll be very aliasy, especially as the camera moves. And we kind of want to avoid that. We basically want to have samples that cover with good proportion to the size of that the pixel is capturing behind it, from the texture. I have better slides for that later. Actually, maybe we can, but the idea is that we generate, we'll see how that can be used later, but we basically generate multiple versions of the same image at different resolutions. And we can do that offline or just in time, but so it's like scale down with a filter. That could be different filters for how to do the scaling, but like a simple filter would be the bilinear filter, which is just taking, in this case, because we're doing a very simple scale down by 2 in width and height, so scale down by 4, so we just take a box of 4 pixels and just average those out. And then we do the same thing again to generate the next smaller version, and we just keep doing that until the kind of the lowest detail that we care about. This is a video that I did of a software render in JavaScript, if you can believe it. This isn't WebAssembly or anything, it's just pure JavaScript. It's a rasterizer with a texture sampling, and you can see this is not WebGL or anything. This is just JavaScript software, pixel by pixel. And you can see that kind of like the smoothing of the texture as it goes, further away from the camera and at different grazing angles. And that's kind of like the idea, that's the goal that we want to do. This is doing rasterization. I will go over both. Let me just see that I haven't missed anyone. Okay, all good. I'll continue. Cool. This is another video showing another software. This is not a rasterizer, this is a raycaster, like the Wolfenstein 3D style. I wrote this in Odin from scratch completely. And this is doing bilinear, and I think in some of these trilinear filtering. Yeah, and you can see that it gets blurry as things move into the background in grazing angles, which is better than very aliasy and very flickery. Anyway, another example. Okay, so in bilinear, I don't know if you can see it with the video compression and the streaming and all that, but there may be a way to see where we'll see it more. There's like slides which show it more succinctly, but there's like lines of seams of where the MIP levels change, basically where it starts sampling from lower fidelity images. Yeah, like here. Okay, so here we can see like 2 seams actually. So like this is, I think, MIP level 0, which is the original or something close to that. And then a smaller version, which is more like blurred. You can sort of see the seam here where it transitions. There's another transition here. So let's say we have this triangle. Let's say we're talking about a rasterizer. Um, and this triangle maps to this image, which is tiled. So it's like different areas of the triangles have different density of UV space, of texel density compared to the, let's say, per pixel, per screen pixel. So here they're more like spread out, and here they're more condensed. What that means is that if you ask the question for each pixel, like how much UV space, like texture area, does it cover? So like, because the as the density goes lower, each screen pixel ends up capturing less texels, and in here it'll capture more texels. If it was the original image, if we didn't have mip mapping. I don't know how much I should go into it. Are people finding this interesting? I don't want to spend too long about it. But basically, the main idea is that we want to find kind of like a relationship between the size of the pixel and the size of, like, how many texels does it capture behind it currently. And we want to do that accounting for this like perspective of the UV space. So we have these UVs assumed to be like interpolated with perspective on all three corners, and then we do like interpolation, and we're expecting this to be representative of like each sample will know what area of the UV to sample from. And we want to basically gauge it such that we want one pixel to kind of correspond to one texel of the sample behind it, ideally. So we kind of want to get closer to it. And with pre-sampled and convolved smaller versions of the image, we can get closer to that. So if here we're sampling a smaller texture, then there will be fewer texels here, which is what we want, because otherwise there will be more here. So we kind of want to keep that relationship close. So there's different ways of doing it. Like in a rasterizer, there's there's like derivatives. I won't go into it because this is not really the topic. But there's like approximations. So here's like a good depiction of what we're looking at. So like for this pixel, we can, if we kind of warp it or unwarp it back into UV space, that's kind of how this edge of this, vector between these two pixels, how it will like backwards project into the UV space. And the same is for here. And we see that this one takes longer because it takes more texture space because it's further away. So like backwards projecting, it gets bigger. And this one is closer, so it's smaller. So this is like kind of a depiction of how it looks when it's like backwards projected. Our triangle onto the UV space, or like the density. This is like an explanation of like how to approximate it. So we have these two vectors, here and here, and we kind of want to estimate the area, the surface area that is being captured here in UV space, and here is capturing more and here is capturing less. And so if we have like a 64 by 64, that's the like MIP level 0, it's a very low resolution texture for this particular case. Then we see that like we have a texel size that is really small. So here is going to have many of them, and here is going to have less. And as we go into higher and higher MIP levels, our texels get larger. So like in here, this is closer to this area, and this is even closer, but like goes a bit beyond it. But like maybe this will fit this one, and then this will fit this one. So if we have a way to like compare those in code when you write the texture sampling, that's kind of like the mental model that you should have to approach the problem. Basically, it's like we can start from here and then we go down until like this starts to be less than a pixel, because here it's more than a pixel, and here it'll be starting to be less than a pixel. Then we like stop. Okay, MIP level 3, that's good enough. And for this one, maybe we stop at MIP level 2, because like here it's still bigger than a pixel. Like if our projected pixel, backwards projected pixel is here, and this is the texel size, and then here maybe it's a little less. So we stop here for MIP level 2 for this guy. So this is how we end up having this seam somewhere over here, let's say, where like this one will be MIP level 2 and this one will be like MIP level 3. I'm gonna pause right now, see if everybody... Okay, we're good. I'll continue. Okay, so we breezed through it. So this is the same thing for a ray tracer, like, and then we'll start talking about what we do there, because for rasterizer we have stuff that are called derivatives, which basically means that like the GPU, or like even in software rasterizer, people can do it. We kind of do like four pixels at a time. Like if we go back to here, 4 pixels at a time. Then we have these vectors that we can do between the pixels, and then we can do like a derivative of basically like what's the rate of change of the size of the texels, or like the sizes of the backwards projected pixels onto texture space. But like for a ray tracer, we don't have that, because we're not even doing projection, we're doing something completely different. So we kind of want something equivalent that will give us the same ability to like backwards project a pixel that represents a sample of a primary ray, let's say, but then we can like continue on with that for like secondary rays, for like reflections and refractions and whatnot. But like for just the primary rays, we basically want to get to the point of being able to estimate what is the backwards projected size of a pixel in texture space. And then we can get through this loop of you know, finding the right one, starting from something that captures too many texels all the way down to, well, now it captures 1 or less, and then we stop. So if we do that, it'll look something like this. This is like an older implementations that I did. I haven't quite gotten to the point of it looking like that for my new implementation, but that's kind of like what I'm aiming. I don't know if with the compression is you being able to see this, but there's like, you can see like a circular thing, seam going on here as the angle changes, where the texture MIP levels change. I have, let's see. I have a video that I did for the rasterizer that shows it. Yeah, so this is the software rasterizer that I have in C, and you can see how the MIP levels are changing. So especially on the plane, it's very obvious to see where those changes happen. It's like a visualization of it, especially as it goes to very low MIP levels, can be very apparent. And if I show what I got right now in my implementation, so this is the ray tracer, software ray tracer, and we have something sort of similar. Like if I go far away, you can see it changes. There's some issues, it's still not perfect, but it kind of gets an idea. And yeah, with streaming and and recording, it's struggling a little bit, but yeah, anyway. Okay, we can continue from current side. Okay, so how do we do this? So we're starting off with a ray tracer. We have the concept of like primary rays. So we shoot primary rays from the point of view of the camera through the center of the pixels for like a real-time ray tracer with one sample per pixel. And it hits some stuff. In this case, it hits a plane, and we can conceptualize like a backwards projection of the projection planes with all the pixels projected onto the plane here. And then the plane itself has its own like UV space, let's say. And what we saw there was because of like where it becomes like a grazing angle, because the rays are emanating kind of like a circular fashion around the viewpoint. We end up with like sometimes with seams that kind of like in a circular fashion. So the idea is, okay, we're starting from a pixel and we're shooting a ray through it, so we can imagine like the pixel getting backwards projected, and depending on the focal length of like the field of view, the kind of projection can be more or less wide. So we are projecting, let's say we hit this plane, and this plane can have all kinds of orientations towards the viewpoint, from the pixel's perspective. So the shape of the projected rectangle in this case can change depending on that. And then we have the texel space represented here with like, let's say we UV mapped 0 to 1 on this thing in a very simple way, and you can see that like the density correspondence is changing based on the orientation. So, and then say we hit something, and then what happens if we want to do like a secondary ray, which we don't have equivalent of in rasterization at all. So we can start off by this from this projection, because we're basically asking like, what does this pixel see, right? When we shoot the ray and hit something, we get a hit point, and our pixel is not zero area, it has some surface area. So if this pixel, this single sample is to be representative of what this pixel sees, then there's this kind of like a surface area of what it sees, represented on this plane here. And then if this plane is reflective, we kind of want to continue from that, and for like the secondary bounce of another ray and hit another surface, and we can continue this projection in this fashion. Okay, so this next part is like an approximation that I did. This covers like an approximation for how to do that. So say this pixel is like 1 by 1, let's say. CW is cone width, and we have like a T value for the ray. And if we look at this triangle here in dotted lines with the green and the purple, so we have a right triangle, and we presumably have like another right triangle. Don't know if I'm drawing it here. Between this and like over here, there's like two right triangles, one inside of each other. The one from the pixel backwards onto the origin where the camera is, and then there's this like proportion, because like if from here backwards to where the camera is like the focal length, and you do this similar triangle thing, you get this proportion. Don't want to get too much into it because the other thing that I want to cover is going to be a bit different, so I'm just kind of glossing over it. But yeah, out of this proportion you can get the, like, it was over 2 because like we're taking like half the width of this thing, right, for this triangle. But like the same thing happens on the other side, so then the like over 2 cancels out, and we're just left with this. But this basically gets us like, what is this? Like if this is 1, the width of the original pixel, and what is the width of the projected pixel, which is abbreviated here as CW for like a cone width. It's like a rectilinear or like a rectangular cone that's being emitted here. Yeah, so like if the pixel size, if we have it even like as a surface area, because it's like it's a square, then we have this T value here from the origin, and we have the focal length, which is here, and we can use that and the original pixel size, and we can compute what is the surface area of this of first this here, not the projected yet, but just the like straight on projected onto up to this point. And then we wanna know what the actual like projected representation here is. So if we look at this thing, we have the normal, and we have the ray direction, and we have this angle between them, and the cos, and it's the same angle here. If anybody did like shading with like Lambert or like Lambertian model for shading, it's kind of like the same thing. In here, what happens in Lambertian, we're like multiplying by the cosine of the angle to do like a foreshortening, basically like making it such that it reduces the amount of light. Here we're dividing because we want to expand the surface area. Am I making sense, by the way? I want to check chat. There hasn't been any comments. Are people still following, or am I rambling? Just want to gauge the chat before I continue. E1. Okay. I'll continue. From current slide. Okay. So, yeah, like so for Lambertian shading, it's like because the surface area grows larger and closer to grazing angles, then the density of the light that's being captured is lessened. So we multiply it. But you can see here, it's like, okay, so this is the like the cone width, the original, and we want this one, and we have a right angle triangle here, and this angle between the normal and the ray direction is the same angle over here. We can prove that easily, and we have this right triangle here, so like this one is the projected cone width over 2, and this is the cone width over 2. So this is the projected cone width over 2 over times cosine this angle, and we can also know that this is the projected cone width, like the original one, over 2. For cosine of the angle, we do like the dot product, obviously, and yeah, and this is the same as the cone width over 2, and from that we can do some simplification and derived what the projected cone width is, which is just the cone width over the dot product. Okay. And then if you want to do like the full surface area, is like the cone width times that, which is that. Okay, so PA is going to be like the projected area. And because cone width is here, and then we square that because we have cone width square. Okay, what are we actually using that for? So we hit some area, and we want to estimate, like our end goal is to estimate what, like texture, in texture space, how does this look? Like how big is this pixel projection in texture space? So how do we do that? So if we know the surface area, like in world units or like local space units, whatever space we're working in, if we know the surface area, like in actual units, and we know the surface area of this sub rectangle, this projected area, if we can compute that surface area, again in world units or whatever space that we were in, then we can ascertain like how much of this surface area is being captured by this, just this over that. Right, this proportion of like the projected area over the entire surface area. And like the surface area, we can even pre-compute if it's like a triangle in a triangular mesh or like whatever the case may be, and we can account for like transformations to account for that. We can like do local space tracing, so we do all the stuff, everything in local space, and then we don't care about transformation. And we can use this proportion because we can say, okay, we also know how much UV space this entire thing is taking, because presumably it's UV mapped, so it's like baked into the mesh. So like this, each corner has a UV coordinate, so we know what is the texture space that this entire thing is covering, the thing that we've hit in its entirety. And then we can say, okay, so this amount, in texture space that this projected pixel, backwards projected pixel is covering in texture space, we'll have the same proportion to this that we have in just world space, and it's the same if it's like oriented, right? We don't really care exactly where it is. The area relation stays the same. So we can say that, okay, so this thing, the proportion of the portion of in texture space that this projected area is taking is this whole thing times this other proportion, that is like how much is this compared to that. And if we do that in world space, we get like a fraction, and then we use this fraction and combine with this full texture space that we know from the mesh or from whatever, and then we know what this size is. And that's the thing we can use as a substitute to the thing that we have in rasterization. And we can continue on from then, and then like for a secondary ray, this becomes like our original cone width, like this one here was before for the primary rays, and everything else just works the same way. And like PA becomes the PA2, etc. Okay, so now I'm going to show a different approach that I was starting that I think is more technically more accurate, and you can go a lot further than that. But so let's say we have this this situation here where this pixel is being backwards projected onto the plane, with the center of the pixel being the ray, like the single ray per pixel that we shoot. And what we can do, we can basically raycast or backwards project the four corners of the pixel onto the plane, and then we basically have the same situation, just with like more accuracy. We can do slightly more approximate. If we take just this, we project just 3 points, and then we compute the area of a parallelogram, which is a bit simpler to compute than like a arbitrary quadrangle, let's say. Yeah, so we can compute this parallelogram, so we can do like a cross product, and then we have the length of the cross product between these two vectors is the area of the parallelogram. But we can do something a bit simpler, because we already have the normal. We can say, well, what rotation would turn this normal down to just the z-axis, let's say. And we can compute a rotation for that process, and like quaternion or matrices. And then we can rotate these two green vectors with the same rotation. And then we basically make it such that this becomes a 2D problem, because we ignore z, because z becomes 0. And then we only just solve, you know, the 2D cross product, the determinant of the 2D matrix, this AD minus BC that comes up all the time, which is a very simple computation, and we have the area of this parallelogram. Okay, so we can do a bit, but we don't want to project too many points, it basically means we're doing more raycasting just to be able to get to those points on the surface. So what we could do, well, we already have one point on the surface. So how about we use that as like the origin of a plane, and do just two more. And the two more we can just take from the prior pixel that we visited, their primary rays, and another one from like the bottom of like the top. And that gives us this area, which is not this area. So it's more approximate, it's less accurate, but like we need to raycast a lot less. So it's like, maybe it's good enough. So yeah, that was the basic idea.